Hey everyone, let's see. Last time I promised that we would get a definition that actually has the word Galois in it, so here it comes. So, a finite, normal, separable, extension, say L over K, is called a Galois extension. All right, so we've learned these various properties, right? Recently, we've been talking about separability. We had normal. Of course, we know about finite extensions also. So one that has these three properties, then we give the name Galois extension. And so, okay, so now we want to figure out, why is this good? Why do we want these three properties? And so let's just sort of work our way up. So let's let L over K be a finite extension. And then let's take, let's just look at the inclusion mapping. So we'll say, and let I from K into L be the inclusion mapping. So now, when it comes to, and remember we've been studying extensions of mappings of this form right here. When it comes to this particular setup, right, where we have a finite extension and that's all we know, then if we want to count the number of extensions, where we extend I to, when we extend the domain of I to all of L, all we know is that there are at most the degree of L over K extensions, right? So let's say it like this: the most we can say is that there are at most degree of L over K extensions of I to a monomorphism from L into L. Okay? All right, fine. So now, what if we add normality? So if we add that L over K is normal, right, then, okay, so what does that mean then? Well, it means in part that every element is algebraic, and so oh, right. Let me write it down, and then I'll kind of say what I'm trying to say. So if it's normal, then for every alpha in L, the minimal polynomial, so m sub alpha, which is I of m alpha, because I is just inclusion, splits over L. Why is that? Well, m sub alpha has one polynomial, one root. M sub alpha has one root, and by normality, then all of the roots have to lie at L, right? So m splits completely over L. Okay, fine. Now if we add this last property right here, so if we add that L over K is separable, then this is by theorem 4.3, and we have that there are exactly L over K extensions of I to monomorphisms. Monomorphisms from L into L. Now, if you notice, any such extension has to fix K, right? Because I is just inclusion, which means that I of any element of capital K, so I of little k, is just going to equal K. Which means that any such extension here is going to fix K. So, note that any such extension fixes K. And so, right, and remember we talked about this, the importance, if you have a monomorphism that fixes K, then it behaves as a linear transformation of L, right, of the vector space L. So, so we can say and so is a one-to-one linear transformation of L. Well, if it's one-to-one linear transformation of L to itself, that means it also has to be onto, so it follows that this extension is also onto. So what does that mean then? It means that any such extension of I to a monomorphism from L to L is actually an automorphism of L. And so, remember automorphism, that's a one-to-one homomorphism of the, in this case, of the field to itself. So let's collect what we just said as a theorem, right? So we essentially proved, or we did just prove this. So theorem 4.8, let L over K be a finite extension. Then our extension L over K is Galois if and only if there are exactly degree of L over K automorphisms of L that fix K. Right? So here's the reason that we like Galois extensions. This is why we like normality, finiteness plus normality plus separability, right? That's why we talked, especially, we did hard work on normality, we did hard work on separability, right? And now combining those two along with finiteness, right, gives us this notion of Galois extension. And why do we like Galois extensions? Because it allows us to count exactly how many automorphisms of L there are that fix K. Now, we're not quite done with separability. We need a way to detect separability, right? How do we know when we're working with a separable extension? And so that's what we're going to talk about next. I just want to start off with a polynomial. So let's let f equal k0 plus k1x plus dot 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 plus k sub n x to the n. It's just going to be a polynomial in some k bracket x. All right. Now, the formal derivative of f is, and we will write this as df, and it's going to be the derivative, just as you learned how to take derivatives of polynomials back in Calc 1, right? So this will be k1 plus 2 k2x plus dot 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 plus n k sub n x to the n minus 1. Where what does 2k2 mean? Well, it just means k2 plus k2. What does nkn mean? It means kn plus kn plus kn n times. So it is exactly the same formula for the derivatives that you learned in calculus, but I'm calling it, and we call it the formal derivative. We don't want to assign any analysis. We don't want to think of slopes of tangent lines or anything like that. It's just this algebraic manipulation that we do. Start off with a polynomial. Here's a formula to create a new polynomial. We call this the formal derivative. Right? We're not really thinking of f polynomials as functions anyways. They're just objects sitting inside a ring. Now, it turns out, though, that all the usual derivative rules hold, right? So all the usual derivative rules hold. The product rule and the chain rule and all that stuff, linearity, all of those rules hold. Okay, so why we need this, or why we might want this, is because, and you may have seen this in linear algebra, the derivative allows us to detect multiple roots, right? And multiple roots, that's connected with separability, right? We would like separable extensions, right? So we want places where polynomials don't have multiple roots. Irreducible polynomials don't have multiple roots. So here's our theorem. So let's let f in k bracket x be a non-zero polynomial with splitting field sigma, and let alpha in sigma be a root of f. Then alpha is a multiple root of f if and only if the derivative of f, or alpha plugged into the derivative of f, equals 0. So you've got a multiple root of a polynomial if and only if alpha is a root of the derivative. And this is not too hard to prove, right? But this is then going to allow us to detect separable polynomials. And really inseparable polynomials, I guess, is a better way to, but actually both, I should say. Okay, so in the forward direction, right, we assume that we've got a multiple root. So since alpha is a multiple root of f, we can express f All right, so we have the f is going to look like x minus alpha raised to the m times g, where m is greater than or equal to 2, and g is, well, it's just somebody in sigma bracket x. Okay, now what's our goal? We need to show that the derivative of f, or alpha applied to the derivative of f, is equal to 0. So now let's compute the derivative. All right, so then the derivative of f, so I'm just going to compute the derivative right here. That's equal to x minus alpha to the m times the derivative of g plus m x minus alpha to the m minus 1 times g. Right, so now let's compute, let's just plug alpha in. So now df of alpha equals, okay, so I plug in alpha in here, I get 0. Because I know that m is greater than or equal to 2, this exponent is at least 1, which means that we get 0 right here also. So that's equal to 0, and that's what we need. So in the reverse direction, we're going to assume, right, that the derivative of f evaluated at alpha is equal to 0, and show that we've got a multiple root. So since alpha is a root of, I think I just want to do f first, yep. So this is f of f. We have that f equals x minus alpha times g for some g in sigma bracket x. So now I'm going to take, I guess I'm going to take the derivative. So then df is equal to, so it'll be x minus alpha times dg plus g. Now, when we plug alpha in, we know that we get 0. So since 0 equals df of alpha, and if you plug add in, that's equal to g of alpha, that tells us that alpha is a root of g. So we have that g also has to equal x minus alpha times some h for some, say, h in sigma bracket x. And now, if I substitute g into here, notice that we're going to have f expressed as x minus alpha squared times h. So now, f is equal to x minus alpha squared times h. And so, alpha is a multiple root of f. Okay, so now with this theorem in hand, we're actually going to characterize separable polynomials. Or, well, I guess we're really going to characterize inseparable polynomials. So, this is going to be theorem 4.10. How much time we've got here? Oh, we're good. Okay, so let's let f be in K bracket X, so we just have some polynomial. Oh, and we want it to be irreducible, so be reducible. Then F is not separable if and only if the characteristic is equal to P, some prime P greater than 0, and F is equal to G of X raised to the P for some G in K bracket X. So that's a pretty severe restriction, right? Being an inseparable polynomial, first of all, requires that you're working in a field of positive characteristic, and then it has to be expressed in a very special way, right? As essentially composition, a polynomial where you plug in X to the P. Okay, so first we'll assume that we've got a non-separable polynomial. So let's assume F is not separable. Then what does that mean? Well, then in the splitting field, we've got some root that is multiples, right? So then there exists a multiple root alpha in the splitting field. Sigma, and then according to our previous theorem, the derivative of F applied or evaluated at alpha has to equal 0. So by theorem 4.9, df of alpha equals 0. Now, okay, so fine. So since since f of alpha equals 0 as well, we have that, so the minimal polynomial has to divide f, and the minimal polynomial has to divide d of f. Okay, but we assumed that f was irreducible, which means that f and minimum and m sub alpha, those are just scalar multiples of each other. In particular, they have the same degree. Right? So since f is irreducible, the degree of f equals the degree of m sub alpha. However, okay, fine. So now we've got the degree of this polynomial matches the degree of this one, but we know that the degree of the derivative is 1 less. At least 1 less. However, the degree of d of f is strictly less than the degree of m sub alpha. And so what does that tell us then? It tells us that the derivative actually has to be the zero polynomial. So we can say, and so d of f equals the zero polynomial. Okay, so now I want to write f out. So writing f equal to, so it'll just be something like k0 plus k1x plus dot 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 plus k in x to the n. We have d of f equals k1 plus 2k2x plus dot 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 plus n kn x to the n minus 1, and this has to be the zero polynomial. Okay, so what does that tell us then? It tells us that every one of these coefficients has to be 0, so it follows that m times km m equals 0 for each m between 1 and n. Well, so what does that tell us? Well, we know that f is a non-constant polynomial, so at least one of the coefficients in f had to be non-zero. Right? So, so since f is not the zero polynomial, or I guess I should say non-constant even, f is non-constant, at least one of these coefficients that's not the constant coefficient has to be non-zero. So since f is non-constant, m sum k sub m is not equal to 0. And so that means that we have characteristic, you can say, and so the characteristic of k is equal to p, right, for some prime p. You know what, let me do this in steps here. What this means is that it's non-zero. Okay, so characteristic k is not equal to 0. But then we say, oh, but we're working in a field, which is an integral domain. Anytime you're in a field, the characteristic has to be prime. So since k is a field, characteristic of k equals p for some prime p. Also, okay, fine. So that tells us then that any of the coefficients here that are where the subscript is a multiple p, right, is going to be non-zero, but it also tells us the coefficients that are not multiples of p in f have to be 0. So we can say also km equals 0 when m is not a multiple of p. So this tells us exactly what f has to look like now. So as a consequence, f is going to look like k0, and then we go along until we find the first multiple of p. So plus k sub p x to the p, plus then the next one is going to be, how do I write this, k sub 2p, k sub 2p x to the 2p plus dot 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 plus some k mp x to the mp. Oh, and I probably no, m is fine, yeah. So that's exactly what we said. Now what we have is characteristic is p, and f is expressed as a polynomial, call it g, where you inserted for x, you replace that with x to the p. Okay, so now in the reverse direction, so let's assume that the characteristic of k is equal to p, and that f is equal to g of x to the p. So then if we look at the derivative, okay, so that's going to be dg of x to the p times p x to the p minus 1. But we're in a characteristic p field, which means that this is 0. So the derivative is the 0 polynomial. So if alpha is a root of f, then of course df of alpha equals 0 as well. And so what does that tell us? It tells us that alpha is a multiple root. So by that's theorem 4.9, alpha is a multiple root, which tells us then that our polynomial f is not separable. So therefore, f is not separable. I want to finish just with a quick corollary. There's nothing to prove for this corollary. So corollary 4.11. If the characteristic of k equals 0, then every polynomial in k bracket x is separable. And so remember a lecture or two ago when I said, if you try to think, if you start thinking about polynomials and say, I'm going to try to find one that's separable, most likely you're thinking in terms of, my brain always goes to fields of characteristics 0, or usually does, and so there's no way, if you're working in a field of characteristic 0, right, if you're thinking of rational polynomials or polynomials with coefficients in the reals or something like that, they're all separable. So this is a good place to stop, so we will see you next time.